So let's also kind of take you back on a bit of a memory stroll to Science 10. So we always said that if an object, if it had the ability to do work either by its position or by its state, it's said to have potential energy. So what you would have looked at in Science 10 is objects having energy due to position. So for example, if I lift a box up off the ground, it is going to gain energy. If I lift myself up off the ground, I'm going to gain energy. This energy is what we refer to as the gravitational potential energy. So it's potential energy that's gained due to the gravitational field. So any object can have gravitational potential energy. And this is the one that tricks people a little bit because there's a little bit of finesse to it. So one of the other things you would have learned in Science 10, and we're going to expand on this point a little bit later, we always said that the work done is equal to the change in gravitational potential energy. So you're looking at the gravitational potential energy, or the difference of it between two separate points. So mathematically, what we would say is that change in gravitational potential energy is the work, and we know work is just going to be FD. Now, because we're dealing with gravitational potential energy, we're dealing with the force of gravity, so we could just write this as mg delta d. Now, on your data sheet, it won't be written quite like this. We are just doing a little bit of a semantics thing, because we don't want to talk about distance. Since we're dealing with gravitational potential energy and it deals with changes in height, all we're going to do is we're going to change that d to an h. We're not doing anything else with that, and we haven't. All we've done is change kind of the notation. That's it. So this is our equation for the change in gravitational potential energy. So the change in gravitational potential energy is given in joules. Mass is still in kilograms. G is our acceleration due to gravity in meters per second squared. If we're on Earth, that's 9.81 meters per second squared. Delta H is going to be the change in height, specifically the change in vertical height. So the conventions we have: if an object's moving up, delta H is positive, gravitational potential energy increases. So if I lift a box up further and further and further, it's gaining more and more energy from the gravitational field, so it's going to have more potential energy. Conversely, if we have something moving down, delta H is going to be negative, potential energy is going to decrease. So we would like to determine the work done on a 2,000 kilogram crate by lifting it through a height of 57 meters. Well, we know that the work done is just going to be the change in the potential energy, or the gravitational potential energy, which we know is just mg delta H. We know the mass. We're going to assume we're on Earth. We know the height. This is going to allow us to calculate the work done. So we got 2,000 kilos, 9.81 meters per second squared, and then we get that 57.0 meters. So we have 2,000 times 9.81 times 57. So that is going to give us a huge number of about 1.11 times, or sorry, 1.12 times 10 to the 6 joules. So quite a bit of work needs to be done, but keep in mind, we're lifting this up quite high. We're lifting it up 57 meters, and the object that we're lifting is also 2,000 kilograms, so that is fairly substantial. So there's going to be a lot of work needed to do that. Now, sometimes we might not be interested in the actual change in gravitational potential energy. We might just be interested in, well, the potential energy at a particular point. So instead, we might have this EP equals mgh. The problem that we're going to run into, though, is what is h? And therein lies the trick. This is something that you would have been introduced to in Science 10, but it's not going to get fleshed out into much detail until this point in your physics career, which is now. And we mentioned this at the very start of the course. When you take a lot of measurements, you are generally quite free to choose where you would like to make that reference from. And what we're going to do here, excuse me, what we're going to do here is we're going to show you what we mean by all of that. And the first thing is, we always want to be consistent in the problem. So where you choose a point of reference depends, it's your choice, but you need to be consistent with it. So we have, for example, this book on a shelf here, and we'd like to measure its potential energy on the shelf. The problem is, though, from what height? Do we want to measure it from the floor? Do we want to measure it from the ceiling? Do we want to measure it from this tabletop? Do we want to measure it actually just from the height of this actual shelf it's resting on? And the question is, which one of those is correct? The answer is they're all correct relative to their frame of reference. So you get to pick where you would like to measure your potential energy from. That is your choice. You just need to be consistent with that in the problem. You also need to tell the person. So you have to say, okay, the potential energy of this book is it's measured relative to this floor, it's measured relative to this tabletop. Like, you have to say where it's measured relative to. Now you might say, well, okay, if we all pick different points, how are we going to get equivalent changes of potential energy? Like, isn't that change of potential energy useless? No. If you measure different points to measure your potential energy from, any change in potential energy, you will all agree on that. So that's why we can still use our change in potential energy formula, and it doesn't care where you measure it from. As long as you're consistent with your measurements, regardless of where your friend picked to base that measurements from, the change will always be the same. The numbers that you use to make it up to get that change will be different, but the change itself will be different. So now, the other thing, and this is something that we will see a little bit more later, a lot of times it's very convenient to choose the reference point where the object is located. So for like the book here, if we said that the reference point was where the book was resting, we would call that our reference point h equals 0. This has the advantage that at that point we would say that the gravitational potential energy of the book relative to this shelf is 0. And that's a great choice of reference point, because then that makes the potential energy at that point 0, and that will simplify problems when we're using conservation of energy. But we'll look at that more later. The only other thing, and I mentioned this already, when we're doing gravitational potential energy, we only care about the change in vertical height. So for example, I have this cart rolling down an inclined plane. The only thing we have to worry about for gravitational potential energy is this change in the vertical height. We don't care about this distance along the plane. You won't see that too often though, but it is just something to bring your attention to. Alright, last little piece here, let's just finish up with a nice quick example. So we have a pile driver. It's going to drop a mass of 550 kilograms from a height of 12.5 meters above the ground onto the top of a pile that is 2.30 meters above the ground. So relative to the ground level, so this time they are telling you where they want the measurements based from. So they're saying relative to the ground, we want to find the gravitational potential energy at its highest point and its lowest point, and then we'd like to determine the change as we lift this from the top of the pile to its highest point. Alright, so at its highest point, we know that the potential energy is just going to be mgh. But the question's kind of hard locked us in there. It said it wants it relative to the ground level, so we have to do our measurements relative to there. At the top of the pile, we are told that it has a height of 12.5 meters above the ground. So at the top of the pile, we can find the potential energy relative to the ground. We have our 550 kilograms, we have our 9.81 meters per second squared, and then of course we have our height of 12.5 meters. So this is going to give us about 6.74 times 10 to the 4 joules. Like I said, relative to ground. Now, at the lowest point, we also are told that at the lowest point, this thing is 2.30 meters above the ground. So for our height, we're going to say it's 2.30 meters. So we have 550 kilograms, 9.81 meters per second squared, and then we get that 2.30 meters. So this is going to give us about 1.24 times 10 to the 4 joules. And again, it's relative to ground. So we've decreased the height, like we've lowered this. We've also seen a decrease in the gravitational potential energy, so that's good. So part C, now it's saying what they're asking for is like, here's our pile or whatever, it's 2.30 meters above the ground. So it's asking for the change in gravitational potential energy to lift this thing from the top of the pile up to its highest point. That's what we're looking for. Now, there's two ways you could do this. We know the potential energy on top of the pile and at its highest point. We can subtract those. You could also use EP, change in EP is equal to mg delta h, because you can also determine the change in height. However you want to do it, it doesn't actually matter. But we want it from lowest to highest, so that change is going to be EP at the highest minus EP at the lowest. So at the highest point, we have that 6.74 times 10 to the 4 joules. And then at that lowest point, we have that 1.24 times 10 to the 4 joules. As I mentioned, regardless of where we choose our reference points, we will always get the same change in potential energy. So if we did these calculations above and we did it, say, relative to the top of the pile, we would get 0 here and we get a different number here, but that change is still going to be equal here. So we get the change of 5.50 times 10 to the 4 joules. So that is the change in potential energy. We could also say that that is the work done to lift this thing from the bottom to the top. And again, no matter where people choose their reference points, we'll have different numbers here, but we'll all agree on this point. So your choice of reference is not that important in the sense like it doesn't matter which one you pick. You will find later some reference points are better chosen than others, but that's something that you will learn over time. That's a skill to be developed.